Hi, I'm Gordon, and this is the second video in a short series on natural language processing, and specifically this project is focusing on term frequency, inverse document frequency methods. In the first video, we read in a small corpus of about 1,300 scouting reports for NHL draft eligible players, and we want to be able to create a model that can read these reports and tell us whether the player who's being referred to is a forward or a defender. And from the first video, you will recall, in certain instances, that information is made explicit, and in other instances, it is not. We want to utilize these vectors that we've created, these vectorized representations of the text, to constitute the data that our model will use to make its predictions. So let's go ahead and take a quick look at a few functions that we're going to need. And I'm not going to go through these in great detail. These are fairly standard issue if you're familiar with machine learning methods. But this first function here that we have is going to provide us with essentially accuracy scores. And we want to get the true positive, false positive scores for our model. And remember, since we're simply classifying forward or defender, since there are only two options, there are certain metrics that are appropriate to that task. I'm going to assume that you've got that knowledge if you're watching this video, and I won't go into great detail on what's appropriate here and why. But here, this first function, we are getting these scores from our model and creating a list. These other functions are simply going to help us print out information, right? So the score itself, or down here, a rock curve. Okay, and if you're wanting to follow along with the code, maybe pause so that you can look at these in greater detail. But going forward, let's dive into creating our model, dividing up our data into train and test and so forth. So we'll start with that. And just want to point toward our matrix, and then whether each player is a forward or a defender. This information is going to provide us with. And now we need to go ahead and split everything up into train and test. We're going to go ahead and utilize train test split, which you should be very familiar with. Training size, I'm going to set at 80%. Wow. I'm not a very good typer when I'm trying to multitask, apparently. I'm going to set a random state here so that I can get the same results multiple times. And we'll go ahead and run this. Great. Okay. And I'm going to go ahead and put together my neural network classifier. And there are certainly different ways of doing this. I think everybody has their own preferences. We're using TensorFlow here, so there are certain things that we do need to abide by. But I'll go through this fairly quickly. If you're familiar with TensorFlow, then the code that I'm using here shouldn't be too foreign. And I'm creating a name for this because I like to be able to compare multiple models. I'm not actually going to compare multiple models in this video, but it's habit. Okay, and here we're saying we want to capture the input shape, essentially. And some of what I'm doing here might seem a little bit redundant. I do it partially because in a more of a deep dive, if we were really trying to find the very best possible model for this data, we would try out multiple things, and some of these redundancies just make it easier to compare multiple different models. So we're going to build a very simple classifier model. If you're familiar with neural networks, you'll recognize that. And the reason I'm keeping it simple is because this is actually not a very complex task. As we'll see, our model is able to do quite well without getting very complicated. Sparse categorical cross-entropy is what is appropriate for loss in this instance. And a simple ReLU activation function is also what is appropriate. There are certainly other activation functions which do just fine as well. We just don't need to get fancy. And in keeping with not getting fancy, our optimizer, we're just going to set it Atom. And let's just say 10 epochs. We really don't need to go farther than that. I don't think, based on my memory of this project, which I've done a few times before, I don't think you actually get better results going further than 10. And let's go ahead and build the first layer. So our input units, simply the, well, go ahead and show you. Input units, 6,549, which happens to be the number of columns in our matrix. That makes sense. You know, that's representative of each individual word that shows up at some point in our corpus. So that's really the total vocabulary that we're working with is our input shape here. Activation, we've already set an object for this, so we're just going to say that's what it is. And I've certainly seen, you know, a lot of people don't like to do what I've done here, where we're creating objects that point to an activation function or loss. It's just the method that I was taught first, and it's what I've found I prefer to do. If we want to make changes later on, it's very simple to just come up here and make them. Anyway. And input dimension equal to shape. Here again is a redundancy, right? We already created shape, and then we said, okay, well, now we're creating units. We can change these if we want to. They don't have to be the same. In this case, we're keeping them the same. I really like using a dropout layer here for this project. It's as simple as it is. It may not be absolutely necessary, but I think for the best results, I would recommend including a dropout layer. Okay. Very simple second layer. We're not doing anything fancy. We're not making it, different in some way from the first layer because we don't need to. And for our output layer, we want 2 units because there are 2 possible answers, right? Forward or defender. And you know what? Just to be consistent, let's do this. Go ahead and build the model. And go ahead and add the first layer, the dropout layer, etc. And we need to compile the model. So here the loss function equals what we've already created up here, sparse categorical cross entropy. Optimizer is Adam. Okay, fitting the model to the training data. Really basic stuff here. Okay, and we want to use that function that we wrote earlier in order to acquire our results, right? So here's the function we wrote. Train and Y train. Okay. Here we want the test results. Okay, great. And just taking a quick look at what's here. These are the inputs that we require when we call this function. And this function provides us, remember, with all of the relevant accuracy information based on the fact that we have a simple binary classification problem. We're calling this function. We want to go ahead and print our raw curve. And it's just more information, right? It's not absolutely necessary to do these things. There we go. Print accuracy is the other function that we wrote right up here. And calling this, we just want to say yes, training results and test results. Fantastic. Okay. Same thing down here. Okay. Go ahead and run this. And looks like in our output layer, units equals 2. Okay, and this is running now. It looks like I likely don't have my GPU on, so this is actually going to take a lot longer than it needs to. That's okay. As we're waiting for our model to train up on this data, let's maybe just back up a little bit and take a look at a couple of things that I think are relevant and interesting. I'm going to go ahead and pull up something that we took a look at last time. Actually, you know what? Let's go ahead. I'm going to show a few things regarding the data that we're working with. So this is the CSV file that I've put together for this project, and it's taken a very long time to put all of this together because I haven't done it in any sort of a particularly fancy way. But here you can see I've just got all of these reports just pasted into columns here, right? And then player names, etc. Something that I find interesting when I look through these reports, some of the words that come up frequently that actually give us a good indication of whether the player is a forward or a defender are not words that we would guess, right? Specifically, the appearance of the word forward and the appearance of the word defender, those don't always just indicate, oh, that's the position that this player actually plays. And I think I should be able to find an example of this. Let's do it this way. Okay, I think this is going to be an example. So this player is a forward, and according to my search, anyway, we see the word defenders showing up in his report. And in this case, it's saying that he has the ability to go around and through defenders. It's interesting that these words can come up in places that we wouldn't expect them. Coming into this project, I anticipated that we would see forward as a word, or forwards even, showing up describing actual forwards, and oftentimes that's not the case. Anyway, I find that interesting. It makes this a slightly trickier problem for our model to solve. Something that I would like to do probably in the next video once we are done with this, and here we're just waiting to see the final results of how this model does. But something else that I would like to do is actually go through using maybe like a random forests model, or even just I think a simple decision tree probably would work pretty well, and take a look at which words really do the best job of indicating the position that the player plays, because I find that to be there are some really interesting results there. Okay, and it looks like it should be just about done. Fantastic, there we go. So we can see, as we would expect with a model like this, it very quickly learns the training data, but it does really well on the test data as well. And consistently, I find these results between about, maybe at the very lowest 91%, and going all the way up. Typically, I've seen it as high as 96, 97% accuracy. And we didn't have to do anything particularly difficult or fancy to make this work. So yeah, I'm going to go ahead and close this video here, and perhaps we'll pick up with one more where we take a closer look at what kind of findings we can pull out of this.